So now that's where it starts getting a bit fishy. It's going to affect a particle regardless of where it is, what it is, what forces are acting on it. Once entanglement occurs, it occurs. So if you measure a particle in an entangled system, as I said before, like superposition for all these things, it will collapse into a specific value. It's stuck there. Yet that information still has to hold true. So that will affect the value of the second particle that is entangled with it. Now this thing is very counterintuitive because in our world, the way physicists for decades have assumed our world to behave is that our world is local. If there is an action and a reaction, there is always a medium through which it goes. And that was like, and this basically is a no-local type of phenomenon. You can affect a particle that is right here, if it's entangled with a particle that is 2 light years away, that other one will change immediately. That's why Einstein didn't really like that theory. And in the 60s, I think, Einstein and a couple other physicists designed a thought experiment and published a whole paper on it and came to the conclusion that the quantum theory was completely wrong. Entanglement cannot exist the way it was described. 30 years later, physicist by the name of John Bell actually disproved that. And 20 years afterward, in the 80s, an actual experiment was designed to prove that our universe is actually no local. Is that entanglement can be produced, can be exploited, etc. So building on these two phenomena, superposition and entanglement, we can theoretically build a whole computer based, like revolving on this, atoms and ions, etc. So there are a whole bunch of the possible designs. Now, that's my personal favorite one, or the photon linking approach. So what you do is you trap a whole bunch of ions altogether, and you shoot a laser beam at them. Okay, sorry. You shoot a laser beam at them so that they get excited, they give off light. Now, this light will be, you can use mirrors to bring it to, let's not get into the details of what a CCD camera is, etc. But basically, what happens is that by exciting these specific ions, they will give off light. Now, these light photons also have a spin, and their spin will depend on the spin that the particle that emitted them has. Now, this can work as a logic gate, one of the logic gates that I mentioned before. I will explain that in a second. Now, logic gates are split into categories. You have the ones that I showed before. You have what are called ultimate gate, or XOR gate. Now, theoretically, it is possible to build any possible circuit using only one type of gate. Now, for these computers, it's completely redundant. The circuit looks ugly. It's not very efficient, etc. It can work, but it's not really appealing. For a quantum computer, we'll most likely not have a choice. So if this approach can allow us to create that specific gate, it's called a controlled NOT gate. We can, starting from there, actually make any algorithm that we design work on this computer. What a CNOT gate is, it takes one input as the control and one as the potential output. If the input is 1, you invert the other. If it's 0, you keep it. Now, how would this work? Now, you have 2 trapped ions. So they're just completely isolated. An ion is a positively charged particle, so if you put it somewhere surrounded by other positive charges, it will just stay there. So they're in a superposition state, so they can either be spinning up, spinning down. That you don't know. So you will excite them using one of the beams. It will give off some light. Now this is a beam splitter. This will collect light from several ions and direct it towards a specific direction, depending on their spin, depending on their frequency. So say, if you obtain 2 photons that are spinning down, you know that these ions will be spinning down. So you know that your input is going to be 0, 0, and you won't change anything about it. And say, if you get your 2 photons to be spinning up, you'll get an input of 1, 1, and then you can use a different type of laser to lock these 2 ions into a state where this one is 1 and this one is 0, which is the output that you want. you get another type of light where you know that the two photons have different spin. That's where entanglements start coming into play. Now you will measure the first one. Once you measure this, it will either be a 0 or 1. If you make sure that these two particles are entangled in such a way that their spinning always need to be opposite to one another, which is theoretically doable. I won't get into the mechanics of it. I don't understand them. But it is possible. So the moment this one is 0, this one will become 1. The moment this one is 1, this one will become 0. And then again, you can use a laser to lock the second one to whichever value you need. So if this is to be put together, then we can really build a quantum computer. Now the question is, why don't we have one already? So we have quite a few challenges before the quantum computing, before a quantum computer has to be put together. When you have a lot of particles put together, they can interact with one another. These are all charged particles. There's an electric force interacting between them, etc. And even though entanglement can kind of ignore that force, if a particle is true, like if a particle is not truly isolated from its surrounding, then your calculation will go wrong. You can't really use this design anymore. So right now we are barely able to, regardless of what design you want to use, we are barely able to entangle about 10 particles together. Now we're aiming for 1,000. So we still have quite a way to go. Another issue is reliable memory. This superposition state, this entanglement state, can only last for a while. Now if it lasts longer than the time it takes you to make that computation, it's okay. But in many cases, it's not. Now there is another issue of computation and error treatment. As you can see, there is quite a balance that you need to find between how many particles you want to put in a computer, how many particles can you in theory put in a computer. There's always a percentage of having an error come up. And there are techniques to treat these errors, to avoid these errors, but that would mean that you need to put even more particles in there. So it's quite a tricky situation. The other type of challenges is really on us, on the guys who design it. Now, regardless of, say, we build a quantum computer, if no one is to figure out how the algorithm that will make it work will look like, then it will be completely useless. We have to figure out the method. The computer will just do the math. Same goes for the logic manipulation, the logic gates. This is theoretical. It has not been done yet. But yet, if we can overcome all these challenges, the applications are quite huge. I call them no computer science because we can't really do that right now. So first one is factorization. How many of you guys got debit card last weekend? Come on, raise your hand. Now, if I had a quantum computer, you guys would all be in trouble. Basically, the way we transfer secure data is by having a security key, which is just a very, very large number that was created by taking two very large prime numbers and multiplying them together. Now, a computer will take centuries to break that code. Right now, a quantum computer can do that in a matter of seconds. Moreover, the algorithm for this operation had already been figured out. So the moment a quantum computer is built, all our security, or most our secure channels of communication will be compromised. However, quantum computers will also allow us to secure our data in a different way. There will be a completely new system of encryption that will basically involve the sender and the receiver sending a whole bunch of photons to one another, agreeing on a code. And that code would be, okay, this is quite a complicated process. I can make a presentation just on it. But this is extremely secure. Moreover, it will allow you to know if someone is eavesdropping on you, if someone is trying to break that code, and act accordingly, completely change the channel that you're using to send messages, etc.